We're now going to look at question 2 of the 2023 A-Level Further Statistics paper. In this question, there are 3 parts. The first part tells us telephone calls arrive at a call center randomly at an average rate of 1.7 per minute. After the call center was closed for a week, in the random sample of 10 minutes, there were 25 calls to the call center. Part A asks us to carry out a suitable test to determine whether or not there is evidence that the rate of calls arriving at a call center has changed. Use a 5% level of significance and state your hypotheses clearly. Is standard hypothesis testing. Let's do this together. You'll find out that parts A, B, and C of this question are actually standalone questions. Therefore, I'm going to just show part A here. As I said, this is a standard hypothesis testing question. So let's take a look at the question carefully and also write out our hypotheses. In our question, we're given the average rate of 1.7 per minute. And in terms of the observed data, we were told there were 25 calls in 10 minutes. Therefore, we need to be quite careful with the parameter being used, whether it's 1.7 or 10 times 1.7. The question is asking us to carry out a suitable test to determine whether or not there is evidence that the rate of calls arriving at the call center has changed. So it's not asking us whether it's reduced or increased. It's asking us whether it's changed, and use a 5% level of significance. Therefore, immediately we need to know that it's a two-tailed test. And each tail, we're looking at 2.5% level of significance. Now, let's write down our hypotheses. Let's call our random variable x and define that as a number of calls arriving in 10 minutes. I use 10 minutes rather than per minute because this is what we are interested in. The data that we're told, the data has given us the number of calls in a 10-minute interval. And from the question, x follows a Poisson distribution, let's call it lambda. My null hypothesis is therefore that lambda equals 10 times 1.7, which is 17. My alternative hypothesis, and this is quite important in this question, we need to write that lambda doesn't equal to 17. So not lambda greater than, not lambda less than, it's lambda doesn't equal to 17, because the question is asking us to test whether the rate of calls arriving in the call center has changed. Okay? So these are our hypotheses, and lambda is our parameter following a Poisson distribution. What we need to do here is simply to work out the probability of x greater than or equal to 25, because the observed data is that within a 10-minute interval, there were 25 calls arriving. You might know that in the tables provided, we don't have a Poisson distribution with parameter 17, therefore we need to use our calculator, but that's not so difficult. So let's try and work out in our calculator, if lambda is equal to 17, what is the probability of x being less than or equal to 24? And we get 0.9594, which means that the probability of x greater than or equal to 25 is 0.0406. Now, we're not there yet, but this is quite important. So you notice that this 0.0406 is less than 5%, but it's greater than 0.025. So if we weren't careful, and if we were using a one-tailed test, using the 5% level of significance, we would be rejecting the null hypothesis. And that would lead us to an incorrect conclusion, because we need to be using a two-tailed test. Therefore, we need to comparing the test statistic with 0.025. The test statistic is greater than 0.025. Therefore, our conclusion is that there's not enough evidence to reject H0, and it's still a 5% level of significance, because importantly, we're using a two-tailed test. That was our part A. Now, let's take a look at part B. Part B actually doesn't require any information from part A. It tells us only 1.2% of the call center lasts longer than 8 minutes. One day, Tiang has 70 calls. Probably asks us to find the probability that out of these 70 calls, Tiang has more than 2 calls lasting longer than 8 minutes. So there are quite a few numbers here in this question. There's the 1.2%, there's the 8 minutes, there's the 70 calls, probability that there are more than 2 calls lasting more than 8 minutes. The 8 minutes here is essentially a red herring. You can ignore that. What we're interested in here is the probability of success, so that's 1.2%. The number of trials, 70 calls. Whether this says 8 minutes, 9 minutes, 10 minutes doesn't really matter because I already know the probability of success is 1.2%. Now, I know the number of trials, I know the probability of success. Therefore, the distribution that I could be using here is the binomial distribution. And let's call our variable y. Y equals the number of calls longer than 8 minutes. Okay? So based on our question, y follows a binomial distribution with number of trials of 70 and probability of success 1.2%. I'm just going to write that out as a decimal. The probability that will give me the answer is probability of y greater than 2. Let's be careful with the inequality sign that it's not greater than or equal to 2 because the question tells us it's more than 2 calls. What is that? Probability of y greater than 2 is simply 1 minus probability of y less than or equal to 2. Let's use our calculator and work that out. Total number of trials is 70, probability of success of 0.012. That gives us 0.9477. And our answer is therefore 0.0523. So that's our part B. Now on to part C. The question tells us the call center records show that 95% of the days have at least one call lasting longer than 30 minutes. On Wednesday, 900 calls arrived at the call center and none of them lasted longer than 30 minutes. This is an approximation to estimate the proportion of calls arriving at the call center that last longer than 30 minutes. It's quite a wordy question, but let's try and write out in mathematical notation what we know and write out our unknown as well. Let's call our unknown C, which is the number of calls longer than 30 minutes. Okay? And because the question is asking us to estimate the proportion of calls, I'm going to call that P. I'm going to set P to be the proportion of calls longer, so longer than 30 minutes. So there is a number, which is C, and there is a proportion, which is P. And we are given the number of trials, 900 on Wednesday. What do we know about the variable C? So we know that C should follow a binomial distribution because we've got number of trials, 900, probability of success, basically success being the call being longer than 30 minutes. The question is asking us to use approximate approximation because the number of trials is quite big. So we can approximate that to a Poisson distribution, which is equal with parameter 900 times P, because we can approximate lambda to be broadly n times P. Okay? So let's see what the question is telling us. The question is telling us the call center records show that 95% of days have at least one call lasting longer than 30 minutes. So the probability of there being at least one call, so C greater than or equal to 1, probability of there being at least one call lasting longer than 30 minutes is 95%. Alternatively, we could say that the probability of C equals 0 is 0.05. So basically, we're saying just 5% of the days, basically that's 0 calls lasting longer than 30 minutes. And that's this Wednesday. Out of the 900 calls, none of the calls lasted longer than 30 minutes. In a Poisson distribution, we know that the probability of x equals x with parameter lambda is simply lambda to the x e to the minus lambda and all over x factorial. Therefore, P of C equals 0 equals 0.05 can be written as lambda to the x, so let's write that out. Lambda is 900 p to the x or to the 0, e to the minus lambda is e to the minus 900 p all over x factorial equals 0.05. That could be written as e to the minus 900 p equals 0.05. That could be simplified to minus 900 p equals the ln of 0.05, which means that the probability I'm interested in, the probability proportion of calls longer than 30 minutes is 0.00333. And that's our answer to part C.